So let's continue our conversation about concentration. Again, this is how we're going to communicate to others the amount of solute that's been added to a solvent to form a total amount of a solution. And that's something that might be limited by the solubility of the solvent. And it's something that might be limited by our choice as scientists that need a very specific concentration. And so we're going to talk now about how to best represent that. And there's a number of ways. So here are some of the common ways of representing concentration. Molarity, here at the top, is the one that we use the most often in a chemistry lab. And it's going to describe the number of moles of the solute to a volume of the total solution. And that volume of the solution is going to be both the volume the solvent takes up, but also the solute as well. And so we use this one the most because it's using moles, and moles is that counting number that's going to help us make predictions about the amount of reactants or products that will participate in a reaction. Again, this all comes back to the fact that in these chemical reactions, we need molecules or atoms to collide for a reaction to take place. So we care about counting the number of molecules or atoms that we have participating in a reaction. But we don't typically see molarity in our daily life. And there's a number of other types of concentration that are out there. So one of them is mass percent, which is like the mass of your solute divided by the mass of your solution. And we do use this one a lot when we are describing the concentration of a solid dissolved in something. Like I weighed out 5 grams of this solvent or solute and added it to my solvent to make a solution. And so this is typically used when it's easier to know the mass of both the solvent and the solute. We use volume percent as well quite a bit when it's easier to measure the volume rather than the mass. And a lot of the times this is when we have two liquids that are combined to form our solution. So you see these percent volume by volume calculate or concentration units when you buy like a bottle of alcohol or rubbing alcohol. It usually has a percentage, right? So if it's like 40% ethanol in your solution of alcohol and water, then you would be using a volume by volume concentration. Then we also have mass percent and volume. This is when it's easiest to report the mass of a solute and the volume of the solution. And so we see this a lot in the medical field where our solution or our solvent in our solution is usually water. And it's easier to measure that solution that forms, which is liquid, as a volume. And then the mass is typically something like a salt or something that can be easily measured out as a solid, like glucose or sodium chloride or magnesium chloride, something like that. So we see mass per volume percent for concentration when we're in more of a medical setting. We also have parts per million or parts per billion. This is a way of describing really small concentrations. So we either have a ratio of mass of the solute to mass of the solution or volume of the solution to volume, or volume of the solute to volume of the solution. But our solute is much, 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 much smaller than the total amount of solution that we have. And so we use this to discuss like sometimes pollution, like we have part per million like tolerance levels for certain pollutants in our water system. That's one. If you're working on something that's very oxygen sensitive, you might track the parts per million or parts per billion of oxygen within a gas environment that a reaction's taking place too. Let's look at the equations for each one of these. So we have molarity is our moles per volume, or sorry, our moles of solute per volume of solution. This is the one that we'll probably use the most in this class. And so it's the one I would like you to be familiar with out of this chapter. Our other types of concentration we'll use more in 162 when we talk about solutions again, but it's really important to know how to handle them then. So we'd like to introduce them now. For any of our compounds that have this percentage, the formula is very similar. So this is our mass by mass, volume by volume, or mass by volume percent. For all of these, we're going to have our solute on the top of our fraction and our solution on the bottom, and they're always multiplied by 100%. And so the difference between these is whether or not we're showing a ratio between mass and mass, volume and volume, or mass and volume. And for these, we just need to make sure that if we're looking at two mass measurements or two volume measurements being compared, that they're in the exact same units. They don't necessarily need to both be grams, but they need to be units that are the same. So if I have the mass of my solute in kilograms, I need to report the solution mass in kilograms as well when I calculate my concentration. Now, the one that is we need a little bit more structure to is our mass per volume. And in mass per volume, we have two different types of physical properties that we're comparing. And so we're going to make sure that we always report this in terms of grams per milliliter. And rather than grams per liter or kilograms per milliliter, which would drastically change the number of the concentration would be presented as. Now, this can sometimes be a little tricky because when we look at these units, these are the same as density. And density can be communicated in a number of different units. It can be kilograms per meters cubed, it can be grams per centimeters cubed, which is the same as grams per milliliter. But when we do that, we usually, or we're often used to seeing it in grams per milliliter. And while the density units can change, because density is a physical property for a compound that doesn't change, we can't do that with concentration because concentration is not a physical property inherent to a compound. Instead, it's something we make. We're like, well, I added this amount to that amount, and that could change depending on what I need to do or how I measured it. So we need to make sure we're always working in grams per milliliter for mass to volume percentage concentration units. All right, next up, we have our parts per million and our parts per billion. And for these ones, they're also going to have a really similar structure in how they're calculated to get the numeric value. As always, we have that solute on the numerator and solution on the denominator. But in this case, we're going to have, we have a mistake. We're going to have them multiplied by instead of 100%, 10 to the power of 6. So that's 10 to the 6th exponent. My superscripts seem to have disappeared on me. Or 10 to the 9th power if we're going to report in parts per billion. So we get that same ratio. We're going to make sure we're using the same units on the top and the bottom of our ratio. And then if we want parts per million, we multiply it by 10 to the 6th, and parts per billion, 10 to the 9th. I'm going to speak in just a little bit more detail about molarity, and then the next lecture video will go over solutions to some practice problems using concentration. And the reason I want to highlight this one is because it's actually the one we are going to use the most in this class, as I said. So molarity is going to be that amount of solute in moles, and it's going to be divided by the volume of a solution. And here's the key part. It's always going to be in liters. So our units for molarity are always going to be moles per liter. And this can be a little bit confusing when you're first learning it because that volume unit is different from molarity than if you were going to report mass per volume percent. Remember, that was milliliters, and this one has to be liters, and they can't get mixed up, otherwise we are off scale in our reported value. So make sure it's moles per liter. And when you use units for molarity, you can use capital M and report it as, let's say I have something that is 5 molarity for a concentration of a solution. Whoop. Sorry about that. I would report that as 5 M molarity. But you can also report it, and it would be correct to say moles per liter for your units. Either one is fine. I personally prefer 5 moles per liter because it signifies to me how I can use concentration as a conversion factor, which we have to do a lot. And if I see a big M, I sometimes will forget exactly what tools I have at my disposal in a conversion. I'll forget that I can use concentration to convert between an amount of something and a volume of something. So let's talk about what happens if you go into the lab and you're going to make a solution. So the proper procedure, I guess, for making a specific concentration of something is to use a piece of glassware called a volumetric flask. And we've got a picture of one here. The cool thing about volumetric flasks is they have only one marking on them to indicate a measurement. And on our example here, it's right there. I'm going to highlight it on all 3 versions of this. And that one marking is has more significant figures, is more certain than something that has lots of markings on it. And so oftentimes with volumetric flasks, you'll see that the volume is, if it's a 10 milliliter one, the marking is 10.00 plus or minus like 0.03, something like that. And so we can get a lot more significant figures in our measurement and have a lot more scientific certainty about the solution that we're creating when we use a more, I guess precise is the wrong word, but we use a more dialed in instrument. So I would take my volumetric flask and I would weigh out the mass of my solute that corresponded to a number of moles that I was trying to add into my solution. I would weigh it out and I would add it into the volumetric flask. Now, for concentration, we are reporting the volume of the total solution. So that's the solute and the solvent. And so I'm going to add then my solvent up until I hit the volume for my total solution. Most likely with the volumetric flask, what you're doing is you're using a flask that's specific to the volume of solution that you need. And so I'll fill that up part way, like we show in our middle one right here, where we have our line up to about here. And then I'm going to swirl it, and it's going to swirl around and around, and I'm going to use a swirling action to mix it until I have a homogeneous solution. And so this way I don't spill because it's such a narrow neck that comes up from it and it's pretty tall. And then once I have a homogeneous solution, then I can fill water up to the marking very carefully and then swirl some more, but I'll have a more homogeneous, more uniform mixture in my flask. So let's walk through an example of a molarity calculation. So in this problem, we're being asked to calculate the molarity of a sodium hydroxide solution, where we're going to mix 0.35 grams of sodium hydroxide with enough water to make a 200 milliliter solution. So I have 0.35 grams of sodium hydroxide, and I'm going to have a 200 milliliter total volume of my solution. Let's go back to what our molarity equation looks like. So molarity is going to be equal to our moles divided by our volume. And specifically, we need to have units of moles and units of liters. I have neither of those. So really, this is going to become a conversion problem too. So I need to convert my solute, which is my NaOH, and my solvent is going to equal water. I need to convert that mass of solute into moles. And I need to convert that volume of solution into liters. So let's do that first. I'm going to start with my 0.35 grams of NaOH. And I'm going to multiply this by the molar mass, the inverted molar mass. So I'm going to have 1 mole on top and the grams on the bottom for my sodium hydroxide. And if I use my periodic table and I calculate my molar mass, I should have a value that is 39.99, let's call it 7. And what this number is coming from is adding up from the periodic table the elements that make up my compound. And so that's sodium, which has a molar mass of 22.98976. Plus my oxygen, which is 15.999, plus my hydrogen, which is 1.008. So when I divide my mass by my molar mass, I'm going to get a value that is 0.0087507 moles. Got 2 significant figures, so I'm going to underline the second significant figure in my value that I calculate. All right. So that gives me my moles. That's going to be a value that plugs in right here. Now to get the volume in terms of liters. So I have 200 milliliters, and I need to be in liters. So I'll put liters on the top of my conversion and milliliters on the bottom. And this is a straightforward metric conversion in one step. Every liter has 1,000 milliliters in it, and so I can calculate a value of 0.200 liters. And I have, in this case, one significant figure. So I'm going to report one significant figure as well. And I'm going to underline it to keep track of it as I move forward. All right. And so this value is going to go into my volume. I'm going to switch colors. All right. So now let's actually calculate molarity. So molarity will be equal to that number of moles I calculated, my 0.00875707 moles of my sodium hydroxide, keeping track of my significant figures, divided by my volume in liters of my total solution. I plug that into my calculator, and I'm going to get a value that is 0.04375, 0.0437535 molar. And comparing my significant figures, the least is the one significant figure in my volume. So I have one significant figure since I'm doing a division problem. I'll use least significant figures. So my concentration for this sodium hydroxide solution is 0.04 molar.